Hi everyone, in this video we're going to work on figuring out what the graph of tangent looks like. So with sine and cosine we focused in on just the relationship between y and t or x and t, and now we want to focus in on the relationship between slope and t. So as our point moves around the unit circle, we have our t and then we have the slope of this line. So we do know how to evaluate tangent using sine and cosine. So we know that tangent t is equal to sine t over cosine t. And we can refer back to that if we need specific values. But just looking at this point, when t equals 0, the point is right here at 1, 0. And if we draw the line through the origin and that point, its slope is 0. So tangent should go through 0, 0. We also have a couple of nice easy points. When t is pi over 4, we're right smack in the middle of this quadrant, which means we're on the line y equals x, and we have a slope of 1. So let's see, let me think about what I want to do here for scale. Let's say this is pi over 2, and this is pi, and negative pi over 2, and negative pi. Okay, so pi over 4, we have a slope of 1. I guess I made this rather steep, didn't I? Let's cross these out. Let's go 1, 2, 3. I think I used my same scale as with sine and cosine. Okay, so pi over 4, 1. And then what will happen, we can check others. We can figure out exactly what our slope is at pi over 6 or pi over 3. But what happens is as the point moves from 0 to pi over 2, the slope gets steeper and steeper and steeper, as steep as we want it, until we hit the point 0, 1, and our slope is undefined. So our slopes are getting bigger and bigger and bigger, but when t is pi over 2, we're getting undefined. So what's happening there is some asymptotic behavior. Bigger and bigger and bigger, infinitely large, and then nothing right at pi over 2. When we switch to the other side of pi over 2, so now t is increasing from pi over 2 to pi, we start getting negative slopes. And right smack in the middle, so this is at 3 pi over 4, we have a slope of negative 1. So we know that we're starting from extremely large negative slopes, and then we're coming in, and at 3 pi over 4 we have a slope of negative 1, so our slopes are getting flatter, closer to 0. And then when we get over to pi, they flattened out completely, and our slope is 0. So we're going to come through and we're going to hit at 0. As our point moves from pi to 3 pi over 2, our slopes switch back to positive, and we start with these small positive slopes, and they get a little bigger, and again right in the middle at 5 pi over 4, we have a slope of 1. And then they're going to start getting steeper and steeper and steeper, infinitely steep, until we hit 3 pi over 2, 3 pi over 2. And at 3 pi over 2, our slopes are once again undefined because we get that vertical line. Okay, and we can continue this, but this is basically the picture for tangent. We could even work our way backwards here to complete another little chunk of the graph. So if we watch our point move from t equals 0 to t equals negative pi over 2, our slopes move from 0 to small negative to negative 1, right at negative pi over 2. Negative pi over 4. So negative pi over 4, negative 1. And then, did I mislabel? I did. This is the pi over 2, and this is the negative pi. Okay, so as our point approaches negative pi over 2, our slopes get infinitely large negative and then undefined. So we're having that asymptotic behavior at negative pi over 2, and slopes getting steeper and steeper and steeper. So the y values of this graph represent slopes on the unit circle. So this is what tangent looks like, and this is actually 2 full periods of tangent. Tangent is an interesting one. Its period is not 2 pi. If you start working your way around the unit circle, you work through all the positive slopes, and then you work through all the negative slopes, and you've only gone halfway around, and then you start back through all the positive slopes and all the negative slopes. So in a full lap around the circle, you work through all the slopes twice. So the domain of tangent does actually have domain restrictions. So this is kind of a tricky one to write. We can work on a little bit of new notation here that we'll use a lot for solving. What we want to say is our input. So I said this was, did I say? I don't think I said. So I said, we'll say it's tangent t. So if this is t and this is our slope, t values, tangent is good for almost all t values, but it's not good for the t values that end at 0, 1, and 0, -1. So the pi over 2s are trouble. So what we want to say is t can't be pi over 2 or 3 pi over 2 or 5 pi over 2 or 7 pi over 2 or negative pi over 2 or negative 3 pi over 2, so on. So we don't want any of the odd multiples of pi over 2. There's a couple different ways to say it. I think what my current favorite is just to say that t cannot equal, and then just pick any one of the asymptotes as the starting place. So I'm going to say it can't be pi over 2. And then what I want to say is it can't be anything that's an integer multiple of pi away from pi over 2. So 3 pi over 2 is pi away. Negative pi over 2 is pi away. 5 pi over 2 is 2 pi away. So the way we'll show this is we'll say t can't be pi over 2 plus k pi, and then we have to get a little mathy here. You can write it out in words if you prefer. You have to specify that k is an integer. So this k and this little backward e looking symbol is element. K is an element of, and then boldface z is the integer. So if you want to write it the lazy math person way, that's the shorthand. It's completely fine to just say k is an integer, write that out in words. That's completely fine with me, but it's very important that you specify. This only works if k has to be those whole number values, those integer values. If k can be a fraction, then all of a sudden we're going to say that it can't equal all these things in between pi over 2 and 3 pi over 2 and so on. So it can't be pi over 2. It can't be pi over 2 plus pi, that's k equals 1. It can't be pi over 2 plus 2 pi, that's k equals 2. And the same with the negatives. Tangent does have some symmetry again. I haven't drawn all of these, but let's see if we go back. 1, 2, 3, 4. There's another branch. It goes like this. And so on. So tangent has that rotational symmetry. If we spin it 180 degrees, it looks exactly the same. Or you could say if you flip over y and x in whichever order, it looks exactly the same. Tangent is an odd function. So what we're saying is that if we have a point on tangent, we'll call it a TM for slope. So let's say this is our TM point right here. We should have a corresponding point with a negative t negative n. So using the opposite t value will give you the opposite slope. And we can see that on the unit circle as well. Let me see if I can get color. I'm really cluttering this up. If this is our, here, we'll just use this one I started with. If this is our t value that gives us a slope of m, then if we go the opposite direction t, you can see that we just get the opposite slope. So this is the same steepness, but it's now negative. So either on the unit circle or on the graph of tangent, we should be able to spot that symmetry. Okay, so for tangent, domain gets really interesting, but range is not quite so exciting, or maybe it's really exciting because the range is all real numbers. So there is no slope that we can't achieve on the unit circle, which means the range is all real numbers. By positioning your point, you can get positive, negative, big, small, everything in between. And then last thing, period, we mentioned is pi. So you want to be really careful with tangent. For sine and cosine, we said if you're trying to look at transformations and you know what your horizontal stretch or compression is, you can apply that to the period 2 pi to figure out the new period. And the same works with tangent, but you're going to be working with pi. So if we want to find the period of tangent and we know that coefficient b, so I'm thinking if I have tangent of bx, then the period is going to be pi over b. So this is all about scaling the typical period by whatever your horizontal stretch or compression is. Because tangent's typical period is pi, we will do pi divided by b instead of 2 pi. And similarly, if we know the period of the new function and we're trying to figure out the b that would make that happen, we would do pi over whatever the new period is. Okay, so that does adjust those two formulas a little bit. All right, so that's the graph of tangent, and just like with sine and cosine, your goal is going to be basically to commit this general shape to memory, remembering that you do have the unit circle to use as a reference if you forget where the asymptotes are or where the intercepts are or something like that. All right, thanks for watching.